Hi, it's me again, and this time I'm gonna present our own paper, Backdoor Indicator, leveraging OOD data for proactive backdoor detection in federated learning. So it's interesting actually. I just present an attack paper, and now I'm presenting a defense mechanism. And we haven't tried our defense, but I believe our defense should be able to defend the attack I just introduced, and I'll tell you why. So this is a joint work with my student, Yanbo. Okay. So I guess previous two talks has already introduced us the background on federated learning, and let's just quickly review. The backdoor attack in federated learning is through the attacker can corrupt some clients, inject backdoors into local models, then through aggregation, inject the backdoor into the global model. Okay. We observe, things I just already mentioned in previous presentation, there are a lot of backdoor defenses on federated learning. However, whenever some defense come out, there are more attacks. Okay, so it seems there's always attacks that is able to circumvent the current defenses. So then we're thinking, why detecting attacks is so difficult? Why the attacker can always find ways to attack or inject backdoor into the FL model? The conclusion is that all existing methods, they are based on comparing model parameters. So they look at the model parameters from the clients. They even they either do some manipulations, for example, clipping, clustering, or adding some noise, DP noise, or they compare the model parameters. They compute some metrics, statistical measures of these models, and say do a outlier detection or a anomaly detection to detect the abnormal ones. However, there's some fundamental problem with this method or this philosophy. Is because just as I think the key idea of the previous attack, the smart attacker can try to mimic or imitate the behavior, statistical behavior of the benign ones, making this kind of defense fundamentally ineffective. Because if my models look exactly like the benign ones, how are you going to be able to detect? Right? And the attacker can always do this in federated learning due to two reasons we identify. One is that due to model non-IIDness, means actually even the benign ones, the local models can be quite distinct from each other. Thus rendering the traditional set of robust aggregation algorithm ineffective, because that is based on the assumption all the data or the models should be IID, okay? And second, taking advantage of this non-IIDness, the attacker actually can, as I mentioned, imitate the behavior of the benign clients, the benign models, such as to circumvent existing defenses. For example, here, by just adjusting the learning rate of the backdoor learning, we can see the true positive rate of detection can be reduced from 100% to 0, meaning like basically the adversary just use a very small learning rate in injecting the backdoor, then there's no way for the server to detect any backdoors. And causing the backdoor accuracy increased from 13% to 83%. And also under the state-of-the-art backdoor defense flame, which is, I believe, also presented in Security 2022. Okay, so then the question we try to answer in this paper is, given this phenomenon we identify, can a defender detect and filter out backdoor updates with consistent performance under different system and adversarial settings? Meaning, no matter what kind of data distribution we have in federated learning and what the attack trying to do to imitate my honest behavior, is that possible for us still to detect with high fidelity? Okay. So the answer is yes. We answer this affirmatively by proposing a proactive backdoor detection mechanism we call a backdoor indicator, pretty straightforward, and achieve this. The idea is for the server to proactively inject, we call it indicator task, into the model using all of distribution data, OOD data. And the idea is that we inject this data, these flags here, and once attacker trying to inject the backdoor, this will fire alarm at the server side. Server can detect, okay, you are doing bad things, okay? Notice here is a complete different paradigm from previous methods. We do not need to look at the model parameters. We do not need to compare with other models. We just take a look at of our indicator task performance. Then we know if you are doing bad things or not, okay? So that's the reason why it's quite effective. Okay, so our construction is based on one key observation, which I'm gonna explain in the following. So first, we observe the subsequent backdoors, meaning like if I inject backdoors multiple times into a model, then the latter backdoor will have some effect on the previous one, okay? So let's take a look. So we perform some pilot experiment to understand this phenomenon. Here, we inject a backdoor task A at TA, and we can see as we continue the benign training, the backdoor accuracy slowly decreases. And then at TB, we start to inject another backdoor TB. Notice there are different types of backdoors. A is a semantic, B is a pixel pattern. And we try to understand how the injection of TB can affect the accuracy of TA. Here it seems to be the effect or the impact is quite minimal, right? Because the TA still continue to decrease. However, we notice here this relationship is actually misleading because we did not incorporate the shift of Bayesian BN statistics here. So BN statistics is a common concept we use to speed up and stabilize the model training. And we collect and compute the running mean and variance statistics in the training data and use them to center and normalize the test data, okay? And we realize here due to the change of the training data, because from TB, we start to inject backdoor task B, and the BN statistics start to shift. But so the estimate mean and variance after TB gradually deviate from task A and is no longer applicable to evaluate task A. So what we do is we save the running mean and variance before injecting TB and use that value to evaluate task A. And see now the result becomes quite different. After we shift back to the statistics of task A, we can see very interestingly, injecting task B at TB actually helps to uphold the accuracy of the task A backdoor. Okay, so this is the fundamental phenomenon we build our defense upon. And the principle or the reason behind this is still not very complete clear to us, but we did some experiment on this. For example, we know this phenomenon is not universal. For example, if we swap the order of A and B, this does not happen. Okay, so still this is an important observation we build upon to develop our defense. Okay, so the key idea. So we just introduced the maintaining effect of the subsequently inject backdoors. And then we mentioned that backdoor samples actually are OOD samples, right? Everybody knows it's actually OOD samples of the main learning task. So we're thinking, is that possible to introduce some indicator task, right? Trained using an OOD data such that because the backdoor task, right, task A is an OOD data and it can be maintained by another backdoor B. So is that possible to actually, for us to design some indicator task using OOD data such that if there is some subsequent backdoor task being injected, then my indicator task performance can be maintained, right? This is the basic idea in our proactive defense. So let's take a look at the threat model. Attackers go, of course, to inject the backdoor into the global model. The capability here we need to emphasize because this is, as far as we know, is the strongest strongest model in the attacker model because we allow the attacker to corrupt any number of clients, like meaning all of the clients. It's possible. It's possible to corrupt all the clients. Of course, this will make most of the statistical-based defense ineffective, and it can inject any type of backdoors. Do not limit that. And it can start poisoning from any global run in continuous fashion. It can start beginning, in the end, doesn't matter. And the defender's goal is to detect the local model, of course, detect the model from, detect the backdoor model. And as usual, the defender here is usually played by the server, should not have access to the raw data and or the data proxy data with same distribution. So this is our method, mainly divided into 3 parts. The first is to construct this, our defense actually can be described in 1 line. The FL server injects the indicator task before broadcasting the model. Then it checks for the indicator accuracy. Right? Then if the accuracy is high, okay, we know something fishy has happened, so somebody inject backdoor into their model. Otherwise, my IAD data, my OOD task or indicator task has a low accuracy due to the forgetting phenomenon. So first part is to construct the OOD data for the indicator task. As we do not know anything about the backdoor type and the triggers as the defender, so we just randomly sample some OOD data. And because we do not know anything about the target label, we just uniformly assign the labels, okay? Then we do before we hand out the global model, we do the injection of the indicator task. Of course, we save the BN statistics of the global model before the injection, do the local training on the indicator data, use the OOD data set we construct, save the BN stats for the detection later, and then replace the BN stats back to maintain the main task accuracy and then broadcast. Then we receive the updates from client. Right? We replace the BN stats. That's necessary from our previous experiment. And then we check because we don't know the target label, so we just check accuracy for all the classes and then find the highest one as our alpha M. Then compare with a threshold, and if it's larger than the threshold, we know, okay, these guys percentually are doing some backdoor into the local model. So evaluation, we evaluate our method and use the metric of true positive rate, false positive rate, and the backdoor accuracy. So we want a high TPR, low FPR, and a low BA, okay? So this is the example of using one like a state-of-art backdoor injection attack algorithm. And we can see for different backdoor types, backdoor types, and in this particular system setting, our indicator achieves the highest TPR, lowest FPR, and the lowest BA. You can see many of the defenses are actually not functioning at all in this case. Okay, and as we mentioned before, when we use different learning rate, the performance of different defenses varies a lot. And for us, we maintain the high detection rate at the different learning rate and low backdoor accuracy. Okay, so for the sake of time, I just skip through this experiment. But to summarize, in all the different settings, we have the best performance. Okay, we have minimal impact on the main task accuracy, and here we want to emphasize here. Actually, we are not sensitive to the source of the OOD data. If we look at this TPR and the BA, even use some random noise at the server and do the uniform assignment, we can achieve like a 90% TPR and only like still quite low. So this is the main accuracy. We do not show the BA here, but still quite high TPR. And compare with the case without the substitute of the BN statistics, you can see for some of the data set, the BA is still going to be affected. So it's important to swap the BN statistics as we mentioned. Okay, so to conclude, we propose the backdoor indicator. It's basically, we consider a new framework or paradigm for backdoor detection in FL, quite different from the previous ones, using the maintaining effect of subsequent backdoors and achieves superior performance in different settings and attacks. Thank you.